for
Chemistry.
Yeah, baby. Yeah.
Hi guys, it's Tom from Let's Get to the Mark. So today we're looking at time of flight. We're going to go through an exam question. Check this out. We're going to look at one of these graphs, how to interpret this MZ graph. We're also going to look at electrospray ionization. Can you describe the process? Finally, in this question, we're going to be looking, can you solve one of these, which is, of course, a calculation on time of flight. You're going to need to remember your speed equals distance over time and your KE half m v squared calculation from physics GCSE. Anyway, enough of my waffle. Let's get to it. Okay, guys, you probably want to pause the video and have a go at this question. All right, I'm going to go through the answers. So time of flight mass spectrometry can be used to analyze large molecules such as pentapeptide, leucine, N-cephalene P. P is ionized by electrospray ionization, and on the mass spectrum, we can see that 556 is the MZ ratio. Describe the process of electrospray ionization and give the equation. Okay, so the first thing with electrospray ionization is to dissolve the sample P in a solvent. You can say methanol or water for this, if you want to give an example of a solvent, or you can just say solvent. The second part of this, is that we need to vaporize it. So what we're going to do is inject it through a nozzle, but also we want to charge it as well. So we're vaporizing it through a nozzle under high voltage. You can say that the end of the nozzle has a current or a positive charge flowing across it. And finally, the sample P gets protonated. That means a hydrogen ion is added to it, or you can say the sample P gains a hydrogen ion. And then we're going to write the equation for that. So how will you show P gaining a hydrogen ion? Well, you'll write P plus H plus goes to pH plus. Now, that means, he says, you can also write that these are in the gaseous form if you want. Oh my gosh, that flipped off. So we can write that this is in the gaseous form because they're all going to be gaseous here. Okay. Awesome. And that should get you your 4 marks. So 1 for dissolving it in a solvent. You need to memorize this, have it on a flashcard. 1 for injecting through a nozzle under high voltage. 1 for protonation or adding a hydrogen ion. And then the equation. I would definitely have this on a flashcard as your 4 points to memorize for electrospray ionization. Okay, moving on. Time of flight mass spectrometry can be used to analyze large molecules such as pentapeptide, leucine, N-cephalene P. Pause the video, have a go, guys. Okay, we can see from the graph that the MZ is 556. This might make us think that the relative molecular mass of P is 556, but it's actually 555. Put a little tick here. Now, why is it 555? Let's go back to our equation from the last question. P plus H plus makes pH plus. pH plus is what's shown on this abundance graph, which is 556. Now, because it gained a proton, that means its mass increased by 1. So P would be 555, H plus is 1, and pH plus is 556, which is shown on the graph. But they're asking us for P, so it's 555. Let's check the next question. A molecule Q, this is the final one of a 10 marker, is ionized by electron impact in a TOF mass spectrometer. The Q plus ion has a kinetic energy of 2.09 times 10 to the minus 15 joules. The ion takes 1.23 times 10 to the minus 5 seconds to reach the detector. The length of flight tube is 1.5 meters. So, ooh, that just flashed up. Never mind. Highlight the key points. So kinetic energy is 2.09 times 10 to the minus 15. The length of the tube is 1.5 meters. And now identify what these units are. So 1.5 meters is the distance. 1.23 times 10 to the minus 5, well, that's time, d and t. And the kinetic energy over here is 2.09 times 10 to the minus 15. So now think about the equations you're going to use. Well, if you've got distance and time, you're going to need velocity over distance and time. And velocity is the linking factor that brings us down to that kinetic energy equation they've put there. So let's write the details in. 1.5 meters is the distance. The time is 1.23 times 10 to the minus 5 seconds. And the answer is 121,951 meters, 0.2195 meters per second. Whew, talk about accuracy. Right. That's our linking point because that's the velocity, and that's going to carry over now to the kinetic energy equation. So we've worked out the velocity of an ion. we need to take that velocity of the ion over to the kinetic energy equation and work out the mass. So let's rearrange this equation. So in order to rearrange this to make mass the subject, we're going to do 2 times Ke. Why 2 times? We want to get rid of the half that's in the equation. So times each side by 2 to get rid of the half on the right. 2 times Ke, and then we're going to divide that by V squared, and that's going to equal the mass. Now remember, we're finding the mass of an ion, but the question wants us to find the relative molecular mass, which is to do with moles. So first of all, we're going to do 2 times 2.09 times 10 to the minus 15 over the velocity which we've got above there. And we're going to square that velocity. Make sure you put this in brackets on your calculator. You don't want it doing any funny tricks on you. And this is going to give us the mass. Now, the mass of the ion here is going to be in kilograms. 2.81 times 10 to the minus 25, and that's kg. When we go to relative molecular mass, remember that is not, and that's for the ion, kilograms in ions. We need to now change that to grams per mole to get the relative molecular mass, because the MR's units are grams per mole to the minus 1. So technically grams per mole. We're in kilograms per ion, which you can tell from the question because the mass is in kg in the question, and the data on the kinetic energy is in ions. So convert the mass to grams first by timesing by 1,000. So instead of 2.81 times 10 to the minus 25, we're going to wipe out 3 of those zeros, as it's going to get 3 times or 1,000 times bigger. So it's going to be 2.81 times 10 to the minus 22. Next, we want to convert this from ions to moles. So how many ions are in a mole? Well, we're dealing with one ion. We need to times by L, or Avogadro's constant, 6.022 times 10 to the 23, which you can see above, and that now gets us in grams per mole. And if we do that, you should come out with an answer, which is bada bada bing bada bung, 169. And if we do the decimals, 169.2, but you could just round it to 169. Both would be accepted, 169 or 169.2. And there you go. There's your 5 marks. And that's a time of flight question. Thanks for watching. If you like any of these videos, please hit the like. That would be nice. Subscribe, share, and I'll be releasing many more. Check it out. See you later.